Let's go straight to the applications. So, as we have seen in the past lectures, we basically covered all the theory we need to now approach concrete physical examples in which we are going to have particles and electromagnetic fields arranged in various ways, and we will see how the two are reacting one with respect to each other. Okay? From now on, the lecture should be kind of, easy going because you already know everything. Okay? All what we're going to do are just applications. A very interesting one, because we're going to start to see how also astrophysical objects behave. In fact, I will first give you the physics itself about the very processes that are governing the emission within the context of charged particles and electromagnetic fields. And then after we have done that, I will give you examples. Jets coming from AGN, galaxy clusters, the Bremsstrahlung emission from the intergalactic medium, which is the intercluster medium that is filling up those objects, and so on and so forth. Okay? And at that point, we will have concluded the block about the emission processes and the behavior of charged particles. Then we will move on again with radiation processes, with radiation transport, where we see how radiation is transported through a medium, or get absorbed and emitted through a medium. For example, if we want to study the emission of a star, which is as a background of a nebula, the medium, the light is going across this medium, and what we observe is not going to be the same as the emission at the origin. And this is going to tell us something about the nebula which is in between. The emission itself of the nebula, if you have like a gas clouds and you have an emission process taking place somewhere, radiation is going through the medium itself, which is generating this radiation. You have again emission or reabsorption within the medium, and what is coming out again reveals us something about the properties of this gas, of this plasma, of this medium in general. Okay? And then we will see quantum processes, because we are going to have atomic transitions as well that are taking place in the cosmos. And actually, they are a super powerful tool to investigate the astrophysical properties of clusters, chemistry of the elements that compose those objects, the velocities, because if we have emission lines, we can measure the bulk motion of those objects with respect to the line of sight. We can see measure the temperatures, and so on and so forth, various properties. But this is coming next, okay? And just telling you where we are going. Now, let's close the box with the emission of charged particles, and let's see some of the applications. The first of which is Thomson, the Thomson scattering and the determination of the Thomson cross-section. What do we have here? Well, we have an electron that is sitting there somewhere. We can define the axis that I call Z, that is pointing in this direction. I have the axis X that is pointing in this direction, and Y is pointing in this direction. Then we have an incoming electromagnetic wave that we assume to be polarized and monochromatic. So monochromatic polarized radiation that is coming along this direction. And you know that we are going to have the electric field pointing in this direction and the magnetic field orthogonal to it. And both of them are orthogonal to the vector EK, which describes the direction of propagation of the electromagnetic wave. Okay? So we have electron, which is free, and then we have a monochromatic, polarized, electromagnetic wave. And that's the configuration. Now you know what's happening. What's happening to this beloved free electron which is sitting there? There is an electromagnetic wave which is going through, right? But what is an electromagnetic wave? It is an electromagnetic field. An electromagnetic wave is just a solution of Maxwell's equations. It's just a specific solution for an electromagnetic field. And what we have in this electromagnetic field? We have an electric component and we have a magnetic component, which are going to be experienced by our free electron. So what is it going to experience our electron? A Lorentz force, right? Which has a component that gives you the acceleration of the electron. So we have the mass of the electron, and then we have the double derivatives, right? That's just the acceleration. If we want to express this guy in terms of beta, again we have the mass, then we have c and beta dot. Okay, you see this way, from a double derivative, we just have one derivative, because beta is the velocity over c. That's why we have this c here, right? And the derivative of the velocity is the acceleration. And the Lorentz force, as you know, we have the acceleration given by the electron. And now, look, there is a minus because the charge of the electron is negative, right? This guy here is the Q that we had so far. Then what we have? We have the component, again minus because the charge is negative, and then we have the acceleration of that is given by the magnetic field. So minus E over C, and then E cross C. But now what we take? We take our free electron, which is non-relativistic. Non-relativistic. What does it mean? That the velocity of this electron is way smaller than the speed of light, c. Which means that beta is way smaller than 1. Do we care about it? Not quite. No relativistic electron, we have V over C, which is our beta, which is way smaller than 1. And therefore this guy is negligible. Not zero, but is negligible with respect to this electric current, because we have this factor 1 over c that is kind of killing that term. Therefore, what is going to be relevant is the electric field. And now what's happening? You see, we have the acceleration that is directly proportional to the electric field. And what is the electric field here? That's an electromagnetic wave. Positive, maximum amplitude, 0, negative, minimum amplitude, and so on and so forth. We have an electric field which is at the position of the electron oscillating in this way. From maximum positive to minimum negative, going across 0. So what's happening? That the electric field at a certain point is pointing in this direction, the electron is accelerated downward. The electric field after a certain point will be negative, and it's going to be, the electron is going to be accelerated up. Therefore, our electron is accelerated in this way, right? We have an acceleration. And what's happening when we have an acceleration for an electric particle, for a charged particle? Well, it's emitting radiation. We've seen that through the Larmor formula. So let's see. We have that the power which is emitted per solid angle, so that's the amount of energy emitted per unit of time per solid angle, is equal to E squared over 4 pi c E cross beta dot squared. That's the non-relativistic expression, right? I can use it straight away because I already said it in first place that is not relativistic. Okay? So during the exam, if you see non-relativistic, go straight to the non-relativistic case. Don't start super generic and then make approximation, unless you need to take care of some aspects, and you will see some fishy business you have to take care sometime. But in general, if you see non-relativistic, take it easy, okay? Make your life simple because you already know that this expression is valid. Okay? Good. So that, now what? We have beta, all right? So we can just plug into here, and we have the emission. E to the power of 4 pi m squared, c to the power of 3, and then the electric field. All right? The electric field is entering through beta. That's what we get. So we know how the particle is emitting given the incoming electromagnetic wave. What is the power emitted per unit angle? Now, if we want to have something more explicit than that, we have this cross product, a bit annoying, so we can set the coordinates such that we can have a better representation, a more explicit expression. So we can see for E, so the direction of propagation of our wave, that's going to be equal to the sinus of theta 0 cosinus of theta. So we start to give few angles. So let's say that we are an observer sitting here. Okay, looking in this direction at our electron, theta is going to be this angle, and the vector E is going to indicate the direction of propagation of the electromagnetic wave, which is the one that we care, right? We are observing from this direction. And then for alpha, now I used a very specific angle. If I want to be more generic and then be taking care of all possible orientation for the polarization direction, right? If you have a polarization emission, is always the electric field and magnetic field are fixed, but you can have a wave coming from this direction or with a polarization angle which is different. Okay? Now I let free the polarization angle. It can be also, arbitrary. And let me draw it here. Let's say that now this is the polarization angle, alpha. Okay? That we will need later on. Because it defines the orientation of the electric field. It tells you where the electric field is oriented. Therefore, we are going to have the cosinus of alpha, sinus of alpha, and 0. Okay? Now that we have E and the electric field, we can compute the cross product. Minus sinus alpha cosinus theta, cosinus alpha cosinus theta, and then sinus alpha and sinus theta. Just applying the cross product, we get a vector, right? Which is orthogonal to the direction of propagation of the electromagnetic emitted wave from the electron, so the scattered radiation, and the magnetic field. Sorry, the electric field. That is coming from the acceleration of the electron. If we now plug our cross product into our expression here, what we get is the more explicit version of this equation, which is the emitted power per unit of angle equal to E to the power of 4, E to the power of 2, 4 pi m squared, C to the power of 3, 1 minus sinus square of theta, cosinus square of alpha. Well, this is coming just from computing the modulus squared of this vector. You see, we have a modulus square, so you just have to do the square, the sum of the squares of these three terms, and that's what you get. Okay? Very simple step. But this is what? This is for an incoming electromagnetic wave. Okay? And we know what is the power emitted. Now, what we can define is the differential cross-section. That allows you to link the power that is emitted per unit of Solling angle, that's why it's differential, because it's the cross-section per unit of angle, is going to be equal to what? The flux, so it is a power, right, per unit of angle, therefore it's going to be a flux per unit of angle, so that's the incoming flux, times an area, the cross-section, that is going to be per unit of omega, per unit of solid angle, right? Let me first write it like this. Don't cancel because I'm going to write it again. We have a power which is defined, which is equal to what? The incoming flux per area. Okay? Because the flux is a unit, is an energy per unit of time, per unit of area. You multiply per area and you have your power. And then we just evaluate it per unit of solid angle. Okay? If you want, this is the definition of the cross-section. So we are asking ourselves, what is the cross-section that allows this construction? Okay, that's how we define the cross-section. To do that, we have the explicit expression. We know what is the incoming energy density flux, which is given by the Poynting vector, because the energy density flux of the incoming radiation is the one of an electromagnetic wave, and is therefore given by the Poynting vector. Okay? And it goes in the direction zeta because we have chosen the axis such that the direction of propagation of the electromagnetic wave is along the direction z. And now what we do? We just plug our Poynting vector into here. This guy, we know, what is it left? The cross-section. And boom, we have it. The signal over the omega is equal to e to the power of 4 m of our electron squared c power of 4, 1 minus sinus the square of theta cosinus square of alpha. That's our differential cross-section. Now look at this guy. This guy is actually the radius of the electron squared, where the electron is considered as in the classical frame. Okay. Another way to look at Re is by comparing the electric energy that we have at a certain distance e with respect to the position of our electron. And we say that this is equal to the mass of the electron c squared. So we are saying, what is the radius at which we have what is the energy? So, what is the radius at which the electric energy is equal to the rest mass of the electron? Okay? Or if you wish, let's find the radius at which the electrical energy is equal to the rest energy of the electron. That's our classical radius for the electrons. And again, don't be misled by the term radius, because we are not thinking at a ball. We are not dealing with a ball. The definition is here. It's all about absorption and re-emission of power. We have an incoming electromagnetic wave, energy density flux, which is absorbed. Right? Therefore, the cross-section is the quantity that tells you what is the amount of flux which is captured by our electron. It's all related to absorptions and emissions of energy. And in fact, you also see that it's not a ball because it even depends on the angle. If you have an electron in this location and you have an electromagnetic field coming in this direction, you have a scattering process because you have an absorption and re-emission in a certain direction according to the angle theta. You see there is a theta dependency. It even depends on from where you are looking at. If you're looking at this from one direction, you see more scattered light, the cross-section is larger. If you look in another direction, you might see less scattered light. The cross-section along that direction is smaller. So it is all emitted to the power re-emitted by our charged particle. And there is an angular dependency. Okay, so do not think at a ball. Okay, it's all about energy. What is the fraction of energy which is captured by our electron. Okay? If you want to think in terms of particles, and you have a scattering processes, say we are considering not an electromagnetic field, but photons, with a scattering on your free electron. Now the cross-sections tells you what is the probability for these electrons to be scattered, to have a collision with the electron. Okay, completely different view, but is the same process taking place. Okay. So we have a number flux in this case because we're counting the electrons, and the cross-section tells you what is the probability, is related to the probability of having such an amount of flux to appear. And this gives you the number of scattering, if you wish, collisions. Okay? Different pictures, but same physical process. Good. Then let's see. This is there is this alpha. Here you see that's related to the polarization angle of our incoming electromagnetic wave. And as I said, we are considering one monochromatic polarized wave. But what is the light in this room, for example? Very likely is unpolarized. Okay, there is not a polarization. And the radiation that we perceive is given by the superposition of all the electromagnetic waves produced by the all surrounding emitting objects. Okay? So let's now see what is the cross-section when we assume unpolarized light. Which means that we have a great number of electromagnetic waves that are hitting our electron with all possible orientations. Okay? Let's see. And so on and so forth. Okay? So we have one wave which is, let's say, in the plane of the board. We have one plane which is inclined this way, another one which is inclined in another way, and the electron is experiencing the superposition of all of those electromagnetic waves. Okay? For what we need to do now, and just continuing with that, we need to compute what is the average of the cross-section, and the average is going to be given over the inclination angle of the incoming polarization waves. Okay? The process that overall is going to be given by the average over the alpha angles, the polarization angles of the incoming electromagnetic wave. Therefore, we get our cross-section, the sigma over the omega, and the average is done with respect to alpha. Okay? And let me just see how you do that. As I said, I already gave you this evaluation. If you have any function with some variable alpha, now we're talking about angles, is going to be given by what? The sum between 0 and 2 pi of our function with respect to alpha. If you have points, you're like summing up numbers, if you want to compute the number, the average of a set of numbers. And you do what? You normalize over the number of entries in your set, right, of numbers. In this case, we have a continuous function, therefore we have an integral over the entire range 2 pi from 0 to 2 pi, and we divide by the entire range 2 pi. That's how we get an average of a continuous function. A set of infinite functions. Okay, each of them has a specific alpha. So let's do that. We now evaluate our average. We just plug in the differential cross-section that we have from here. And we get the radius of the electron over 2 pi. The 2 pi is coming from here by the averaging processes. Between 0 and 2 pi of 1 minus sinus square of theta cosine square of alpha in the alpha. And now you just have to solve this integral. Again, do it in front of a fireplace in one of these cold evenings. That's a trivial process that I'm not going to do here, so I just give you the result, which is this one. That's the integral between 0 to 2 pi of this function multiplied Re over 2 pi, which is the average cross-section given an incoming incoming radiation which is unpolarized, superposition of all possible waves with all possible polarization angles. Good. Then what? This is angle, and this is useful because if you have the dependency with respect to theta, you know what is the efficiency of the process, if you wish, given your position with respect to the electron. You have the incoming flux of radiation. Now it's given by the superposition. You are sitting here. The electron is oscillating somehow, given the all kicks that are given by all incoming electromagnetic waves. There is an emission which is given by the Larmor formula, and what you get is a certain amount of scattered radiation, right? If you are in another position, you see a different amount of scattered radiation. If you are in a different position, you see a different amount of scattered radiation, and this is given and is parameterized by this theta angle, your direct orientation with respect to the free electron. Now let's try to look at the total cross-section. So it's going to give you what is the amount of flux that is captured that is going to be scattered by the electron. And it's going to be what? Well, we need just to make an integral over all possible angles. Therefore, we get our function, the sigma over the omega of omega, and we now integrate over all possible angles. All solid angles, right? Theta is just an orientation, but it is axially symmetric. So you need to then integrate over the entire direction. You also have scattering that are going to taking place in this direction, right? You have a scattering electromagnetic wave. It might be scattered in this direction. Right? You have a fraction of that energy that is scattered in that direction as well. Good. So we just plug in our stuff. We compute our integral over the entire solid angle over 2. Now we integrate between 0 and 1. That's because as a variable in the integral, I can use the cosinus of theta instead of theta. It is just simpler. Just make your life simpler. Okay? I just relabel the variable. You can call it u, right? And this would be u squared. Okay? It's just a relabeling of variables. So I'm just doing the integral over the cosinus of theta, and it goes from -1 and 1 because these are the extremes of the cosinus, or the entire possible angles. And the result, again, is just the integral to be evaluated, is this one, that we call Thomson cross-section. Okay, isn't it simple? Now, let's look for an example, right? Let's take a more massive particle, a bigger particle. Let's take a proton, for example. Let's take in more general, let's even be more general. Let's take an ion, okay? Ion and the cross-section must completely respect all this prescription. The only thing that is going to change is the mass and the charge. That's it. All the rest is going to be the same. So if we take also a look at the last results, everything is the same except for the charge and the mass. And we see that the total cross-section is directly proportionate to the radius, the classical radius of the particle that we are considering, which is directly, so that's directly proportional to the charge square. So now I call it Re. E is not an index, it stands for ion, okay? It's equal to now the charge square over NEC square to the power of 2. But the charge is given by the charge number of our ion, which is usually indicated with Z. So Z is the number of charges that you have in your ion, and each of them has a charge. As we know, if they are going to be protons, they're going to be the same charge of the electron E. Over the mass of the ion, C squared, all of it at the power of 2, which gives you a Z to the power of 4 and E squared, and then the radius of the electron. Well, now, let's give a look at typical astrophysical plasmas, okay? In astrophysics, what do we have? Typically, we have that 75% of all what you get is hydrogen, plus basically the rest, 25%, is helium. Of course, that's not the full picture because we exist, right? And we need silicon to stand on a planet, we need oxygen, carbonium, and so on and so forth, carbon and so on. And all the rest in astrophysics, you speak about metals. See what a simplified mind we have? Okay, so we have hydrogen and helium, the rest are metals. It's just a name, okay? But in the jargon, everything which is not one of these two elements are called metals. And they're quite rare with respect to the totality of the universe, because these numbers come up from the primordial nucleosynthesis, so at the beginning, after the first 3 minutes, within the first 3 minutes after the Big Bang, all the elements have been produced with this ratio, roughly. Okay, a little bit of beryllium and lithium, but in very few traces and nothing else. Then you got the formation of stars. Stars start to, through nucleosynthesis, through nuclear fusion, start to get these simple blocks, put them together, and produce new elements. Okay, up to iron. Then more massive stars that arrive at producing iron, at a certain point can now produce higher, more heavier elements. That's because for the fusion to take place, for such a massive elements, you need a an endothermic reaction, not an isothermic. Therefore, you need to give energy to the star to do that. Nobody is giving energy to the star. Therefore, the star says, guys, I cannot. I can only produce energy myself, building up blocks up to the iron, more I can't. And therefore, I stop burning, producing energy in the core. What's happening at this point? You have your star, you have your boiler that is keeping your star well blown, okay, like a balloon. You switch off the boiler, the energy is not there anymore, gravity is the only ruler. The stars collapse. Okay? You have a core collapse supernova. There are a lot of processes taking place, among which a huge release of neutrinos that are going to blow up, among other processes, the star. You get a supernova explosion. And within these explosions, you get the production of even higher, more massive elements with respect to the iron. That's why we have gold, that's why we have all the elements that are composing ourselves, okay? And the rest of the universe. But the percentage that is produced is little with respect to that. Then you can say, well, okay, we call them metals because they are negligible, right? In an astrophysical process, who cares? No, because actually those elements can influence, the amount of those elements can influence a lot the formation of further stars, for example. If we have a nebula which is more or less rich with respect to the presence of metals, this nebula might be more or less efficient in producing other stars. Okay? So they are few, but they are extremely important. Okay? As we are important as well, because we need them to produce life. Okay? Good. Anyway, going back to the Thomson scattering, going back here. And this is the typical scenario that we have, but for a good example that we can consider, since 75% of our free ions are given by protons, basically, let's give a look at the case of hydrogen. For the ion is going to be a proton, right? If that's the case, the mass of the proton is going to be 2,000 times the mass of the electron. No. And Z is equal to 1. There is one proton. Okay? We now compare the scattering with an electron that we consider up there, is 8 pi over 3 Re to the power of 2, and we look at the more generic case, we can evaluate what is the radiation pressure of electrons and ions. Okay? The difference between the two. And as we have seen, the force produced by the radiation pressure is equal by the force associated to radiation pressure is given by the pressure times what? The cross-section. You see the relevance of the cross-section? Okay? Pressure times area is a force. Now you know what is the force applied to electrons or to ions, depends what you are considering here. And you see that the cross-section of protons and ions, of electrons and electrons are extremely different, one from each other, because there is the dependency with respect to the mass and in general with respect to the charge number. Okay? We now plug in these numbers. What we get is that the force experienced by an electron is actually 2,000 times to the power of 2 the force experienced by an ion. You see now that I'm not talking about balls when we are speaking about cross-sections within the concept, the context of Thomson scattering. The protons, or that you can imagine as more massive particles, and therefore you can imagine as bigger, is actually a smaller cross-section. And why? Because it's more massive with respect to the electron. Let's give a look at the very first equation that I wrote. If I take the acceleration, what is proportional to? At the Lorentz force divided by the mass. Therefore, the larger the mass is, the smaller the acceleration is. Therefore, our particle, if it's more massive, it's shaken less. Our ion is oscillating gently. The electrons, for the same incoming electromagnetic wave, is oscillating way more. And therefore, is emitting more power, meaning the cross-section is larger with respect to the one of the ion, of the proton in this case. Okay? 2000 to the power of 2. It's huge, it's tiny. The cross-section of a proton with respect to the one of the electron. Okay? And you see, again, not balls, but it's everything referring to emission processes, to how the particle is accelerated and how the particle is emitting radiation through the Larmor formula. Okay? For what? These are the two concepts. In the other steps, what we did was to use the acceleration such that we can explicitly compute the Larmor formula. That's what we get here. Okay? Then what we did was to define the cross-section through this equation. So we know that the power that is emitting is directly proportional to the incoming flux. It's reasonable. Twice the incoming flux we get, twice is going to be the power emitted. Times an area, because this is an energy density flux, we multiply it times an area and we get the power. And we define it as the cross-section, which is responsible and associated only to these emission processes and absorption processes. Once you do that, you basically get your expression, and you see how the classical charge of the electron pops up in your expression. Then what we did, this was done for one incoming electromagnetic wave, polarized. What we did now was to consider a radiation field which is given by the superposition of all possible orientation angles for the polarization of the individual waves composing that radiation field. Okay? Unpolarized light. Therefore, what we did was just to integrate getting the average over all possible orientation angles for the direction of the polarization angle. And we arrived then, after integrating over all over all solid angles, because all of that was done per unit of angle, to the total Thomson cross-section. And then, having this very generic expression, we can just generalize our approach and assume, we can now have the freedom to assume a generic charge, and any mass, according to the particle that we are considering. And here, in the example that I gave you, if we take, for example, fully ionized hydrogen, you have your free electrons, you have your protons, and you know that the cross-section of the protons is 2000, the cross-section of the protons is 2000 times to the power of 2 smaller, you see, to the power of 2 smaller with respect to the one of the electron. And this is super important, as we are going to see in the derivation of the Eddington luminosity that I'm going to do after the break. Okay? So we can start at 15 past 10.